Here are our solutions to homework set number 2 for ECE 376. The first problem looks at assembler with APIC processor. What are the contents of your registers after each instruction? So assuming that the W register is 7, register A and B are 5, A and B are just some spots in memory, W is actually the working register on the PIC. The first command says take W, add 9 to it, put the result in W. So 7 plus 9 becomes 16. The second instruction says take W, add it to A, put the result in A. So 16 plus 6 is 22. A changes, W and B are unchanged. The third one says take 3, subtract W from 3. So 3 minus 16 is negative 13. So it's negative 13 or plus 243. Both numbers are identical. This is 2's complement, so either answer is correct. A and B are unchanged. The next one is take B, subtract W from B, put the result in W. So B is 5, W is minus 13, or 243. 5 minus 13 is 18. If I do 5 minus 243, I also get 18. Again, this is 2's complement math. Let's see, 22 and 5 are the same. If you take 5 minus 243, I'll get negative 256 minus 18, well, negative something, which is the same thing as plus 18. Next one, take A, add it with W, put the result in A. So A is 22. In binary, that's 0001, 0110. W is 18. 18 is 00001, 0010. Add them together. Wherever both bits are a 1, the answer is a 1. So here they're both 1, here they're both 1. The answer is 12x, which is 18 decimal. And finally, the last one is do an OR. Take W, OR it with B, put the result in B. So W is 18, B is 5, OR it together. If either bit's a 1, the answer is 1. So the answer is 17x, or 23 decimal. That's problem 1. Problem 2 is act like a C compiler, or act like your own C compiler. Convert the C code to assembly. Well, the first part is I want to reserve 3 spots of memory. Each one's 8 bits, A, B, and C. So I can do that with the compiler directive. Just assign A, memory location 0, B is 1, C is 2. These are really arbitrary. Anything in the first 3.9K of memory is fine. Now do this operation. One way to do that is start with the number 3, add B to W, add C to W, add C to W again, put the result in A. That's one solution. There are others. Problem 3 is suppose A, B, and C are integers. Now repeat. So this is an 8-bit processor. It does 8-bit operations really well. 16-bit operations are a little bit harder. So one way to do that is to store 16 bits. 16 bits don't fit into 8, so I'm going to call 2 locations. This will be A and A plus 1. It takes 2 bytes to store each variable. This will be B and B plus 1. And the result goes in a 16-bit register, C and C plus 1. So to do that, I'm going to take the number 3, move it to C, that's 03. So 3 goes to A. So 3 goes to A, and 0 goes to A plus 1. So there's 3 and 0. Now add B to it. I'll take the low byte of B, add it to the low byte of A. Take the high byte of B, add with carry to the high byte of A. Repeat with C. Add the low byte of C, add the high byte of C. Repeat. Add the low byte of C, add the high byte of C. So this gives you 3 plus B plus 2 times C. This works really well when you're multiplying by small numbers like 1 and 2. If there's bigger numbers, I can use the multiply command. In this case, it's actually a bit harder because adding twice is actually easier than multiplying by 2. In that case, same as before, I'm going to take a and a plus 1, and start with the number 3, which is 0, 3. 3 goes to the low byte, 0 goes to the high byte. Add b to it. Now, I've got the very number c. C's got two parts, called the c low and c high. Take the low part of c, multiply by 2. When I multiply, I get two answers, the product low and product high. Take the low byte of c times 2, add it to a, so add the low bytes, add the high byte with carry. Now, take 2 times the high byte. When I do that, that gets added to the high byte of a, and there is an extra 8 bits, which I don't have any place to put because I don't have 24 bits for a, so I just lose it. Take the high byte of c, multiply by 2, add it to the high byte of a. That'd be using the multiply command. Here you can see this is actually easier. This works really well when you're multiplying by 1, multiplying by 2. If I want to multiply by 73, this is probably better. Problem 4. Convert the following flowchart to assembler. And my flowchart didn't show up. Correction, that was problem 5. Convert the following C code to assembler using an if statement. So first I'm going to assign 2 spots of memory for 2 8-bit variables, A and B. Take A, and it with 0f. That's the following commands in assembly. Move 0f to W, and the result with A, put the result in A. Then an if statement. If A is equal to 0, B is 0. I'm going to use the compare skip if equal command. That compares register to W. So to do that, I'll first set up W equals 0. Here's my register. W is 0, compare A to W, skip if equal. If I skip, I want to do B equals 0. That's clear. Otherwise, go to label 1. Label 1 is A equal to 1. So move 1 to W, compare to A, skip if equal. If it's equal, I go over here, B equals 1. Move 1 to W, move W to B. Otherwise, I go to label 2. Label 2, if A is equal to 2, move 2 to W, compare A to W is equal to 2, skip if true. If it's true, B is 3, move 3 to W, W to B. Otherwise, go to label 3. If A is equal to 3, B is 7, move 3 to W, compare A to W. If it's true, skip. Move 7 to W, W to B. Otherwise, go to label 4. So that would be this code. It's kind of like a case statement as well. Problem 5. Convert the following flowchart to assembly. The first part, I've got a variable called count. I'm going to need it. So put that somewhere in memory. Let's call it address 0. Convert this block to assembly. To make port B input, I need to write FF to tris B. To make A, C, and D output, I clear tris A, tris C, tris D. This arrow is a label. I want to keep looping as long as RB0, port B pin 0 is 0. That's this command. If port B pin 0 is 0, I don't skip. I keep on looping it back to loop 1. When it is not 0, meaning when it's set, I skip. Go to label 2. So here's label 2. Here's label 1. At label 2, I'm going to check if port B pin 0 is equal to 1. If it's not 1, meaning if it's 0, I skip out. So if it's 0, I skip out. If it's 0, should be set. If it is 0, I go to label 3. So if it's a 0, I don't skip. I go to label 3. Otherwise, I count mod 6. So to do that, I'm going to increment count, put the result in count, then check. mi equal to 6. Move 6 to W. That should be a CP FS LT. Compare skip if less than count. Is count less than 6? If it is less than 6, go back to label 2. Otherwise, go back to 0. On to label 3. Move C to A. Move D to C. Then move count to D. Go to label 1. So that's problem 5. On problem 6, convert this flowchart to assembly. So the first one, port B is input, move FF to tris B. Port C is output, go right here, and clear count. CLRF count. I then have a label. This is label 1. I am going to keep looping if port B pin 0 is 0. Port B pin 0 is 0. I don't skip, I keep looping. So that's that block. Next block. If port B pin 1 equals label 2, label 3, label 4. If port B pin 1 is true, go to label 2. So if button 1, this test, keep if clear, port B, comma 1. If it's clear, I skip. If it's set, I don't skip. Go to label 2. Check button 0. Bit test, skip if clear. If it's clear, I skip. Otherwise, I go to label 3. If I skip, I go to label 4. At label 2, increase count by 10. Move 10 to W. Add W to count. Put the resultant count. Go to label 4. Label 3, increase by 1. That's an assembly command, increment, count, put the resultant count. Label 4, move count to port C. And label 5, keep testing as long as port B pin 0 is equal to 1. So if it's equal to 1, I don't skip. Wait till I release the button, then I skip out, go back to label 1. So that's problem number 6. Problem 7 is a hardware question. I've got a thermistor. The resistance versus temperature follows this equation. It's an exponential where the resistance drops as temperature goes up. At 10 degrees Celsius, I want the output to go high. So I want kind of this operation. At 10 Celsius, the output goes to 5 volts. Below 10 Celsius goes to 0. So first thing I do, let's assume a voltage divider, convert resistance to voltage. If I assume a 1K resistor, at 10C, the resistance is 2002 ohms, the voltage is 3.335 volts. So I want to turn on and off at 3.335 volts. As temperature gets really, really hot, R goes to 0, voltage goes to 0. So to be on when it's hot, I connect to the minus input. And the on temperature is 3.335 volts. So here's what it looks like. When the voltage is high, it's really, really cold. When the voltage is low, it's really, really hot. 5 volts when it's hot. Switching at 10 degrees Celsius. That's a comparator. A Schmidt trigger is I want the on and off temperature to be different. So I want to turn on at 15 Celsius. I want to turn off at 10 Celsius. Come up with a circuit that does that. Again, I'll assume a voltage divider, a 1K resistor, and R. First find the voltages at 10 and 15 Celsius. So at 10 Celsius, R is 2002 ohms. My voltage division, 3.335 volts. So that's right here, 3.335. At 15 Celsius is 1576 ohms, or 3.05 volts. And what I like doing is the circuit really cares about voltage, not temperature. What this one really looks like is this. If I put the voltages increasing as I go to the right, just makes me confused when it doesn't do that. here's what you want. You want to turn on at 3.05 volts, turn off at 3.335 volts. When the on temperature is less than the off temperature, connect to the minus input. The on temperature is your offset, and the gain is the ratio, output over input. The output changes by 5 volts as the input changes by 0.3 volts, 18 to 1. Make this an 18 to 1 ratio. And make these much, much bigger than 1K, so I don't have too much loading. Actually, this is a little bit wrong. When I calculated this resistor, I ignored all this. In actuality, there is a resistance over here, so this is actually R in parallel with 191K. That changes the circuit, that changes these voltages, so this is a little bit wrong. Make these large as close, or if you want to get really closer, throw in a buffer. That's an op-amp with a gain of 1, like this. The input impedance for an op-amp is about 4 gigaohms, basically no loading. That'll make it even closer. So here's a Schmidt trigger that turns on at 15 Celsius, turns off at 10 Celsius. The last problem is come up with a circuit that does this. Turn on when I'm between 10 Celsius and 15 Celsius. Now, if you've had electronics, you can do some trickery. What I'm going to do is have a circuit that does this. That's this guy. It's low for temperatures less than 10C. This circuit is low for voltages above 15C. And if either one is low, the output is low. So this is a min function. That's kind of one way to do trickery using electronics. Use a min function, set these up so that the output is low on these two bands. So the top one takes care of temperatures above 15 Celsius, it's off. The second one, temperature below 10 Celsius, it's off. Using a min function. That's one way to solve it. And these are just comparators with the two voltages we found from before. Second way is anything you can do in hardware, you can do in software. I can just have two comparators. This tells me the temperature is bigger than 10C. This tells me temperature is bigger than 15C. And then encoding. If the temperature is less than 10C, I want to turn off the output. So if RB0 is 0, RB0 is 0, I don't skip, I go to off. If RB1 is 1, but 15C, I want to clear the output. If RB1 is set, I don't skip, I go to off. On off, I clear the output, otherwise I set the output. This will also give you the same circuit. So a couple ways of doing it. Anything you can do in hardware, I can do in software. Here's a hardware and software solution. Here is a hardware solution. And that's homework set number 2 for ECE 376.